Hello, this is lecture 5, stat 135. You have a quiz next Friday. It will have 3 problems. 2 problems will be similar to homeworks 1 and 2, and 1 problem will be a mom calculation. So last time we introduced mom and talked about mom's consistency. Today we're going to show an example of calculating mom and also look at non-parametric bootstrap to find a 95% CI of a population parameter, and also finding the standard error of an estimator by hand. So an example of a mom calculation, this is number 16a, chapter 8, but let's first review the gamma distribution. So the gamma density has a variable part. We note that the integral of the density is 1, and so we get this identity which will be useful to us in this example. So let's consider an IID sample of a random variable with density given as shown, where sigma is a positive number. Find the mom estimate, sigma hat of sigma. So we have a single estimate, we have a single parameter, so we only need to find one moment. So let's find the smallest one first. So we find the expectation of x. However, because the integrand is odd, the expectation is 0, and so that's not going to be useful to us since the expectation needs to be a function of sigma. So let's try the second moment. Here, because it's an even function, we recognize the integrand as being the variable part of a gamma 3,1 over sigma, and then conclude that the second moment is 2 sigma squared. We solve for sigma in terms of the second moment, and then use the sample moment to give us the mom estimate. So now let's talk about a non-parametric bootstrapping and confidence interval of a population parameter. This is actually from section 8.5, but I'm doing it here because you have a lab today and I want you to practice doing this in R in lab. So recall that to calculate a 95% CI of the population mean by hand, you need an SRS so that we have a formula for the variance of x bar, and the sampling distribution needs to be normal so that we can find the 2.5th and 97.5th quantile of x bar. Well, this is very restrictive. So often the sampling distribution isn't normal, and perhaps you calculated you collected your sample a different way. So we're going to do this using R. So let's first talk some theory about what a 95% CI is for a general population parameter. This will mirror what we did for the population mean in chapter 7. So let's take a look at theta hat minus theta, which is a random variable. And suppose we know its distribution. I'm not going to assume it's normal. Then what we're looking for is the 2.5th and 97.5th quantile, which we'll call A and B respectively. So what that means is that the probability that theta hat minus theta is between A and B is 95%. We can rework this with some algebra to write this as the probability that theta is between theta hat minus B and theta hat minus A is 95%. And the interval theta hat minus B, comma theta hat minus A is called a 95% CI of theta. Now, theta hat minus theta is only known to Tyche, the goddess of fortune. We don't actually know what it is, but we can approximate it. And and hence approximate what A and B are. So that's what we're going to do next. So here we have a procedure. Step 1 is we take a sample, a size n, x1 to xn, and we're going to use this sample to resample from in further steps. But I just want to illustrate that this sample has an empirical distribution, and if the population has CDF-F, if the population if the sampling distribution theta hat has CDF-F, then the empirical CDF is given by Fn, which is 1 over n times the frequency that your xi is less than x. So, for example, if x1 is 1, x2 is 2, x3 is 3, and x is 2.5, then the empirical CDF, F3, of 2.5 would be 1/3 times the number of xi that is less than 2.5. I should write here 2.5. Which is 1/3 times 2, because 2 of our data is less than 2.5. So the CDF F is shown in purple here, and we're approximating it by the empirical CDF, which is shown in green here. And as n increases, Fn approaches F. So basically, restricting the fact that we're sampling from our original sample is going to become less of a problem as n gets larger. So in step 2, we're going to resample from our sample 1,000 times with replacement and of sample size n, and compute the sample estimator, and we'll call that theta 1 star to theta 1000 star. And so we're going to subtract our original estimator from each of these, and that's theta 1 star minus theta hat, and so on up to theta 1000 minus theta hat. And we're going to find then in step 4 the 25th and 975th largest value from this list of 1,000 numbers. And this is an approximation to the 2.5th and 97.5th percentile of theta hat minus theta. And then by our work above, the 95th percent CI is the interval theta hat minus B to theta hat minus A, where theta hat is the original sample estimator of theta. A and B are the 25th and 975th largest numbers on our list of 1,000 values. So now you're going to practice this in lab. So I'm going to go back now to section 8.4, and I'm going to talk about actually computing the SE of these estimators by hand. So it's unlikely that you'll be able to find the 25th and 97.5th quantile of theta hat, even if you know the distribution of theta hat. So usually you're just happy to be able to compute the SE, so you have an idea of variability of theta hat. So we're going to take a look at an example of this. So theta is a parameter determining the distribution of x, and the standard deviation of x, which we denote by sigma, is hence a continuous function of theta. So we can think of it as theta as a function, sigma is a function of theta. So for example, x being Poisson lambda, the SD of x is the square root of lambda. So sigma of lambda is the square root of lambda, a continuous function of lambda. Now, if sigma is continuous, then as your estimator converges in probability to theta, which we know happens for a mom estimate because it's consistent, then sigma theta hat will converge in probability to sigma theta. So sigma theta which is unknown, it can be approximated quite well by sigma theta hat, which is known. So let's take a look at an example here. You have an IID sample is taken and you collect data, let's say 47423, which follows a Poisson lambda distribution. Let's find a mom estimate of lambda and approximate the SC of your estimate. So x is Poisson lambda, okay, and you can see that the SE of lambda hat is the square root of the variance of lambda hat. Now lambda hat is x bar, so that's the square root of the variance of x bar, which is the square root of the variance of x over n. Now to calculate the variance of x, well, we don't know what the variance of x is, but we can approximate it. And so there are two ways you can do that. One is you know that x being Poisson means that the variance of x is just lambda, and lambda we can approximate by lambda hat, which is 4. Another way is that the variance of x is can be approximated by the sample variance, which we can also compute. But the sample variance is a little bit more laborious to compute. So instead of 4, you would get 14 over 4, which is close to 4.